Getting to orbit with any vessel in Kerbal Space Program is a challenge that should not be understated. Players often make many mistakes in attempts at suborbital flights before they reach a stable low orbit. The road to efficient orbital launch is a long, punishing ordeal, ripe with uncertainty. Moreover, every vessel flies differently. Hard-learned rules from flight testing with one vessel might prove useless or even counterproductive with other vessels. So to talk about designing an automated control system capable of landing on the moon is to set the bar pretty high. The good news is, aiming high is kind of the point. Normally, it takes a lot of staging and clever redistribution of mass and fuel to coordinate a lunar landing. In the interest of eating the elephant in smaller bites, this exercise uses a vehicle with a modified engine. Our resident rocket scientist adjusted the aerospike to boost the exhaust velocity up to about 10% of the speed of light. The resulting engine has enough thrust to take off from sea level on Eve and enough fuel to accelerate at 1G for a little over a day. This makes it a little easier to design our automation system. No pesky staging to interfere with our script. But enough about rocket science. This is about computer science. Any sensible solution likely involves breaking down the problem into smaller chunks we might be able to tackle individually. This is a process called decomposition. While it shares its name with the process of death and decaying organic material, that is precisely the outcome we wish to prevent. It is worth noting, in the vacuum of space, there is no organic decay. Mostly we just turn into frozen, desiccated meat bricks if things go horribly wrong. Basically the worst freezer burn imaginable. But this is about robots, not meat bags, and we're hoping to make robots who protect the meat bags and deliver them safely to a totally inhospitable environment, because that's what they wanted. Before we dive into the various phases of the mission plan, let's establish some rules. Ideally, each time we wait for a condition to be satisfied, we want the smallest number of components in our logic. Now, this means using simple conditions whenever possible. Also, we don't want to over-constrain the operational parameters, or the system may not converge toward the conditions and be forever stuck in a loop. For example, most of the conditions in this experiment use single-edge bounded constraints, like wait until periapsis is greater than a threshold. These simple constraints increase the chance of overall system stability, as they are less sensitive to unexpected side effects. Our first step is to escape the gravity well to stabilize into low orbit. This is pretty much as simple as going as fast as we can while staying below transonic speed in the atmosphere. This specific craft has its aerodynamic center co-located with its center of mass to enable atmospheric reentry, with its engines pointed retrograde, without inverting and impersonating a badminton birdie. Plummeting headfirst into a swan dive into the dirt is the exact opposite of our desired outcome, so it's helpful if we can orient the vehicle regardless of the environment. Because we've decomposed our larger problem into smaller ones, it's worth noting these represent discrete phases of our launch and land objective. As we review the script in detail, you'll see this represented by the run mode variable. For example, run mode 1 engages our engines at a safe thrust, and once we reach a threshold velocity, we transition to run mode 2, where the launch profile maintains a thrust-to-weight ratio of about 1.25 during the ascent. This is the slow, gentle climb up to our target altitude of 80 kilometers. Once we push the apoapsis to our target altitude, we cut the engines and switch to run mode 3, where we coast up to the apoapsis. Just before the peak of ascent, run mode 4 engages, and we raise the periapsis up to our target altitude to circularize our orbit. Once we have a stable circular orbit, we move into run mode 5 and begin the process of computing a transfer orbit to the moon. Using this script, we could launch at any time and still find a valid transfer orbit. This is because we rely on the known delta V requirement to make the trip as we consider possible transfer points along our orbit. The script does this by creating a maneuver node and evaluating the resulting orbit. If the maneuver results in an encounter where the lunar periapsis is above ground, we have found a viable transfer point. Otherwise, advance the node by 10 seconds and try again. Eventually, we find an intercept and we move on to run mode 6. With the valid intercept course plotted, we wait until the maneuver time and then execute the maneuver. There are several ways to do this. In this case, we compute a target scalar velocity and engage the engine until the velocity reaches the target. And if we've done our homework, this should result in a transfer orbit with a moon encounter with a subsequent lunar orbit matching our desired parameters. Now we engage run mode 7, where we manipulate time to advance to the lunar encounter, as the transfer itself takes about a day of real time. Once we arrive at our encounter with the moon's sphere of influence, we activate run mode 8 to begin circularizing into a lunar orbit. We advance time again to bring the vehicle to the periapsis, where we engage the engines once again in retrograde to drop into an elliptical orbit with a low periapsis around the moon. Once the periapsis falls below its target threshold, we cut the engines and wait until we coast down to the periapsis. Here, we have one more retrograde burn to stabilize into a circular orbit around the moon. The design uses a lunar orbit of 20 kilometers to reduce the impact of in-game time warp constraints. At this altitude, we engage run mode 9 and wait until we reach a longitude threshold before initiating deorbit. In this case, the specific value was chosen based on manual scouting. It was important for filming to have a landing in the sun. The first landing was indeed in the dark, and it wasn't very camera friendly. Much better to land on the sunny side, where the audience can see it. I'm sure there's a positivity metaphor in there somewhere. But you're more interested in the landing logic. So, the deorbit phase completes when we detect the vessel's ground speed is below a threshold. At this point, we transition into our final run mode, the hover slam. I found an example KOS script from an engineer at SpaceX who was kind enough to share the code. Hover slam is simple. Control the throttle during powered descent such that the velocity and altitude reach 0 simultaneously. I was extremely pleased with the hover slam phase, which was fortunately the most reliable part of the experiment. Now that we've reviewed each part separately, let's put it all together as a time-lapse of the best attempt. For what it's worth, I really enjoy this cloud mod, as it adds a rich context and a sense of realism to take these recordings really to the next level. Okay, so we've reviewed all the parts individually and seen a full example of the mission from beginning to end. And by now, I'm sure you're excited about outtakes. Like, how did it fail? It turns out it failed in several very tightly clustered groups. Let's take a look. First, it failed on over-constrained logic conditions. This version of the script does not show all the terribly stupid things I did in earlier examples. For one thing, I had an extra phase dedicated to lowering the periapsis immediately on entering the moon's sphere of influence. This extra phase added complexity without adding much value, so I settled on the simpler version you see here. I also had weird logic errors which didn't manifest until late in the script. Much like the earlier pioneers of space travel, we don't have the luxury of resetting a virtual environment to retry with different code. KSP does not offer the ability to simulate any scenario without first doing all the hard work to get there. The most common failure I encountered was misinterpretation of conditions upon entering the lunar sphere of influence. The script frequently went rapid fire through the lunar circularization sequence, often skipping important parts and leaving the vessel spinning out of control. Automating time warp was a critical aspect of standardizing this behavior enough to make meaningful recordings. Using manual time warp led to unpredictable results in the script itself. By automating timing in the script directly, the system behavior was substantially more predictable. With a stable trigger for a landing sequence, the script was able to achieve impressive results with tight grouping on the final landing locations. In every case, the landing was successful, except for one instance where I landed on a steep incline and fell over and rolled downhill for a long time before I exploded. But other than that, everything was pretty great. So let's watch a grid of the 16 best attempts all together at the same time. And if you're interested, you can check out this same video in real time without time lapse. And as always, thanks for watching Kerbalism.